Hi, everybody. I'm going to get started now. Can someone confirm that I can be heard?
Yeah, we can hear you.
Okay, thanks very much. Okay, so have a couple of announcements first. There will be a quiz this coming Thursday, so please see Canvas for description of the content of that quiz, what subject matter will be covered, and the logistics for the quiz. The problems on the quiz will be very similar to those in homework and lecture slides and lab. So that's where I encourage you to focus your studying. And there will be some extra office hours for questions and answers this coming Thursday at the same times that I hold office hours on Monday, namely 2:30 to 3:30 and 5 to 6. I'll also mention that some people ask questions in the little mini survey at the end of the homework about a particular question in the homework, namely the one with the glass slide placed in front of one of two interference slits. And I just want to remind everybody that I did post an example question that was just like that in the slides. I didn't get to them on Thursday, but it's fairly straightforward to follow. So I encourage you to go to those slides if you still have questions about that kind of problem. And if questions remain after looking at it, you still have them, please post the question to Piazza or send me an email. Okay, so today we are going to talk about double slit and diffraction grating intensity. Talk about how one would measure distances smaller than one wavelength of light, and indeed distances smaller than the diameter of a proton over 1,000, so very tiny distance, like 10 to the minus 20 meters. And finally, if we have time, we'll talk about what's different between the way your face looks in a mirror and the way it looks to a person who's looking at you. Oh, and I'll remind everybody that if your your Penn State user ID, starts with the letters SE to TE, that you are encouraged to ask questions for extra credit. You can just put the questions into the chat. Okay, so I think we did this concept question last time, but let me just review it in case we didn't. So the idea behind phasors, which is what we're using to figure out the intensity of interference and diffraction patterns, is the phasors allow you to do the superposition of a set of waves that have a fixed phase difference with respect to one another. So if we have n wavelets produced by a single slit, and that's what's shown by this figure at the upper right. Each of those wavelets, and there are 6 of them drawn in here, but of course there are an infinite number. Each of those wavelets travels a slightly extra distance to the faraway screen compared to its neighbor as you move down from the top of the slit to the bottom of the slit. And so each wavelet is represented when it reaches the screen by a wave equation that has a fixed phase difference with respect to the other waves. And so we want to add up all of those together. But the first thing we did was the simple case where this phase difference was 0 because the way we drew the phasors was to have them all lined up with 0 angle in between one phasor and the next. And the question was, if that's what the phasor diagram looks like for a whole bunch of waves, then what angle must these waves be making with respect to the faraway screen? And the answer is that must be making an angle of 0. So in other words, this angle in here must be equal to 0. if the phasors are all lined up like that, because having the phasors all lined up means that there's no relative phase difference between one phasor and the next, and therefore there's no relative phase difference between the individual wavelets that they represent. And the only way to have that be the case for a situation like this is for each of the wavelets to be traveling the same distance as it goes from the slit to the screen. And the only way for that to happen is if the angle there is 0. So then we proceeded to extend this to the case where we're at some finite non-zero angle along the screen. And in that case, each of these individual wavelets will have a little angle relative to its neighbor. There'll be a little extra distance that each neighboring wavelet travels compared to the one above it. And that will result in a phase difference between each wave when it reaches the screen. And that phase difference is expressed by the wavelets having angles with respect to one another. So we have one wavelet like this, and then the next one like that, and the next one like that, and so on. They have a fixed angle with respect to one another. And if you go through the somewhat detailed but fairly straightforward trigonometry, and this is done in the text, you can show that the single slit intensity is given by this expression. It depends on some base intensity, and it's modulated by a factor that looks like sine of alpha over alpha squared, where alpha is this pi ay over lambda L. And notice that it includes this term A, which is the slit width. So this is really a diffraction effect. It depends on the width of the slit through which the light is traveling. You can also show that for a double slit, where each of the slits is identical, so they have diffraction, but there's also interference going on, that there's an additional term that needs to be multiplied that depends on the distance d between the slits. If you put those two together, you end up with a pattern that looks something like this over here. So let's just go through this one image at a time. So this top image shows what you get from a single slit. So you see this, this bright central maximum, and then the first minimum, the first dark fringe on either side, and then there's a secondary maximum here, and then the second dark fringe is over there, and so on. So that's the pattern due to a single slit. Now, if we take a copy of that slit, we have two of those single slits identical side by side, and we have them separated by a distance that's roughly like 6 or 7 times the size of the slits themselves. Then we'll get an interference pattern. That's what each of these little bright fringes is due to. That's due to the interference pattern. But it's underneath the diffraction envelope. So you can see, for example, that right here, where there's a dark fringe, we also get a dark fringe in the overall pattern, because wherever you get destructive interference from diffraction, even if you have two slits causing interference pattern that would otherwise be maximal there, since each of those slits is producing a minimum due to the diffraction, the result is going to be a minimum at that point. So effectively, the diffraction pattern suppresses the interference pattern. Just like in the middle here, you see, for example, a dark fringe right there. There, the interference pattern has a 0. There's destructive interference, and it suppresses the diffraction pattern, which would otherwise be bright there. So the net result is shown in the figure down below, where we have these fast wiggles due to the interference pattern. And that interference pattern is not just, a flat set of wiggles that looks like this, all the way across the screen. Instead, it's got this modulation due to the diffraction effect. So I'm going to draw it on top of here, and you'll see it in a second. So there's the diffraction envelope that causes this interference pattern to be suppressed in some places and allowed in other places. It's basically suppressed everywhere we go off of the central maximum, but it's suppressed to varying degrees. And right around m equals 6 or 7 or so, you can see that the diffraction minimum sits right on top of 1 or maybe 2 interference maxima. So you don't see those interference maxima. Those are called missing orders. And there's another missing order over here at 13, and I guess over there as well. Can't see it beneath that little icon. So this pattern that we see here and that was drawn again here are what you get when you combine the effects of diffraction and interference. So we can do an example problem that involves this effect. And let me read this through and then we'll work it out together. So a student performing a double slit experiment is using a green laser with a wavelength of 530 nanometers. She observes that the m equals 7 fringe does not appear at a position y equals 1.6 centimeters from the central maximum on a screen that's 1.5 meters behind the slits. So she quickly figures out why that's the case and then uses that to determine the width of the slits. So what did she realize and what is the slit width? So what's shown here is the same drawing I just showed you a second ago, where these missing orders are highlighted. And what the student realizes is that the 7th order fringe is missing because it lies under the first minimum of the diffraction pattern due to the width of the slits. So it's the width of the slits causing the diffraction pattern, and it results in a missing order here and symmetrically on the other side. And so she doesn't see the m equals 7 fringe, which is a distance, if she's measuring on the screen, 1.6 centimeters from the central maximum. So it's basically this distance here, delta y is 1.6 centimeters. That fringe is not seen. So how do we figure out what the slit width is based on that information? So in order to do that, you realize that the position of the first diffraction minimum is given by this expression. That position y is lambda L over A. And we know what that position is because we don't see the 7th fringe. So we know, therefore, that the first minimum of the diffraction pattern must be at that value of y, where the 7th fringe used to be, which is 1.6 centimeters. So we just set that y equal to 1.6 centimeters, and then we can simply solve for A because we know what lambda and L are. And if you do that, you get 50 microns for the size of the slit. So next, I'd like to talk in a little more detail about intensity and what it means. So the intensity of the light from an ideal double slit, so there's no single slit diffraction here, so temporarily forget about diffraction. It's the square of the amplitude, and it has this form here. So I'll remind you that the amplitude we wrote down earlier, and it's derived in the text, looks something like this, where E was the magnitude of one of the phasors, and then they had a phase difference of delta phi between them, and so the resultant vector phasor labeled E had a magnitude or a length that was given by that expression there. And then we square that in order to find something proportional to the intensity. And if you work through the details, you see that the two-slit intensity is equal to 4 times the one-slit intensity times cosine squared. So the question is, how is this possible, and isn't the factor of 4 a problem? I mean, you would kind of have expected that the two-slit intensity was equal to just 2 times the one-slit intensity, right? Because you have light coming through 2 individual slits. So whatever the intensity is coming through one slit, if you've got 2 slits, you expect double that. But instead of seeing this, we see this. So should we worry about that? It looks like maybe energy isn't being conserved, for example, because instead of seeing a factor of 2 there, we're seeing a factor of 4, and the intensity is related to the energy. But no, in fact, energy is still conserved. What interference does is it effectively just redistributes this light energy, and it takes the light that without interference would be uniformly distributed on the screen, and it causes it to have this pattern here where it's bright in some places and dark in others. And in fact, if you look at this pattern, it depends on the cosine squared. If you take an average of that intensity across up and down the entire screen, then you end up having a term. If I take the average of both sides here, you end up having a term that is the average of the cosine squared. And so I have the average of the 2 slit is equal to 4 times the average of the 1 slit times the average of cosine squared. And the average of cosine squared is equal to 1/2. So there's the factor of 1/2 that we needed in order to get back the factor of 2 that we expected earlier, because this 1/2 times this factor of 4 will give you 2. So the average of the 2 slit interference, the average intensity from 2 slits is equal to double the average intensity from 1 slit, which is sort of what we expected. And shown over here in this figure, you can see that the intensity peaks at 4 times the intensity for 1 slit, but that the average, which is this line drawn in the middle, is double, 2 times the intensity from 1 slit. Now you notice that this figure as drawn is for an ideal double slit, so it doesn't include any diffractive effects. If we include diffractive effects on top of that, then just showing the interference fringes that are inside the central maximum of the diffraction pattern, we would see something that looks like this. So you still have the energy redistributed, but now the energy is redistributed over an even wider range. Well, the energy is redistributed in a different way, I should say, because you see this diffraction envelope is superimposed. And by the way, there are more bits of this diffraction envelope above and below the screen, as I've just tried to sketch in there. They're just not shown in this figure. Okay. So the last thing I'd like to talk about regarding intensity is extending our discussion for the 2 slit case to the N slit case. And I remind you that the N slit case is interesting because N slits describes diffraction grating, which can have many, many, many slits, thousands of slits in it. For the 2 slit case, we showed that the maximum intensity was equal to 2 squared times the intensity from a single slit, 4I1. You would expect, therefore, that the maximum intensity in general is equal to N squared times the intensity from 1 slit. So That is indeed the case for an N-slit grating. The intensity, the maximum intensity, grows as the square of the number of slits. So you can imagine this getting pretty large pretty quickly. And again, though, energy is conserved. So the total amount of energy that comes out of these N slits has to be equal to N times the energy that comes out of any single one of them, if they're uniformly illuminated on the other side. So what that means, therefore, is that these peaks that are produced on the faraway screen after the light goes through the diffraction grating must be really narrow, and the light energy must be concentrated in smaller, very small width fringes on the screen in order to conserve energy and in order to satisfy the fact that the maximum intensity goes as a square of the number of slits, because each slit produces, via a phaser, some intensity, and those all get added up and then squared in order to get the total intensity. So that's where we get this N squared factor from. And the conservation of energy tells us, therefore, that if we're going to have these gigantic peaks, they better be really narrow, so that the total amount of energy that's light energy that's on the screen is conserved relative to how much was initially input on the other side of the diffraction grating. Okay, so I'd like to summarize the distinctions between single slits, double slits, and gratings. So the thing that they have in common is that they all, one way or another, are due to interference taking place. The differences between them is that for a single slit, the light from various points along the opening of the slit undergo interference with one another. And so you end up with this expression that, remember, we could only derive for destructive interference in the case of a single slit. We could not derive an analytic expression like this for constructive interference. But if you want to find where the constructive fringes are, where the bright fringes are, you could just look in between two destructive angles. So if you solve for where the dark fringes are using from a diffraction pattern, you can find the bright fringes because they're going to be right in between dark fringes. For a double slit, light from one slit interferes with the other one. So the expression that we got looked like this for constructive interference. And if we, in this case, we could analytically solve also for destructive interference by just replacing that integer m with m plus a half. So that way the waves from one slit would have traveled a half integer number of wavelengths relative to the other, and you'd get destructive interference when they reach the screen. And in this case, in the double slit, the individual slits also experience diffraction. So you have to add those two effects together. And finally, for the grating, this was interference involving many slits. And the expression that we wrote down is very similar to the one for two slit interference. And this is, again, for constructive, for where the bright fringes are. The light also here experiences diffraction at each slit. And the light ends up being very bright at the fringes that it reaches by this, this n squared factor for a grating. Okay. So next, I'd like to describe an application of interference, in this case of light. It's something called an interferometer. The basic idea is to use this interference to our advantage. And what's done is that we take a light source, and that's indicated over here on the left-hand side, and we send it towards a beam splitter. And the light then travels, part of the light travels up to mirror 1, a distance L1, and then back down to the beam splitter, again a distance L1. And some of that light will then manage to go through the beam splitter and be detected by this disembodied eyeball here. In the meantime, light from the source can also go through the beam splitter and travel along this other path horizontally, a distance L2 going out and then a distance L2 coming back, at which point some of that light can reflect off of the beam splitter and travel down again to the detector. So what you see is that light can, in principle, travel a different distance along the vertical path than the horizontal path. And if that difference in distance traveled is such that the waves, when they meet at the detector here, is an integer or a half integer number of wavelengths, then you'll get constructive or destructive interference respectively. And in fact, if you move mirror M2 gradually, either to the right or to the left, then you should see interference and interference patterns where you see constructive, then destructive, then constructive, then destructive interference as the mirror moves to the right. And in fact, I have a video that shows just that. Let me bring that up. So this was done at MIT, and they have the following experimental setup. So at the left there is a red laser, and that shines into the beam splitter. And the light then splits up, and some of it goes to this adjustable mirror, the shiny part of which is on the other side. And then a movable mirror that can be changed by moving that micrometer knob. And then the light is sent off to a screen that's basically behind what we were just looking at. And now what the person is doing is moving the movable mirror. And as a result of that, I don't know if you can see this, you see this, this pattern on the screen that was changing as the mirror was moving. And it was changing because you saw bright fringes and then dark fringe and then bright and then dark. Now these fringes here are circular because of the geometry of the setup, but you saw these fringes moving as the movable mirror was translated along its track there. So let's do this a little more quantitatively. And in particular, I'd like you to take a look at this concept question. So the question is asked, so what is the general condition for constructive interference? And remember that the light that comes from the source and goes, say, in the upward path towards mirror M1, travels a distance L1 up and then L1 down. And the mirror, the light going towards mirror M2 horizontally, travels a distance L2 to the right and then L2 to the left. And then those light rays travel the same distance here together. So that's essentially not relevant for the interference effect because there's no additional distance that one light ray travels compared to the other there. So the question is, what is the condition for constructive interference? And I will launch the poll now so you can answer the question. Okay, get your answers in, please. All right. So we have a fairly even distribution between C and D, and a fair number of people choosing other answers as well. So let me ask the following question. What is the path length difference that light traveling in the vertical direction in this figure goes relative to light that goes in the horizontal direction? The light in the vertical direction travels a distance 2L1, and the light in the horizontal direction travels a distance 2L2. So that's the path length difference of light that goes in the vertical direction versus light that goes in the horizontal direction. And those factors of 2 are there because the light goes up to the mirror distance L1 and then down again. And on the horizontal, it goes from left to right, the distance L2, bounces off the mirror, comes back and travels another distance L2. What should I set this equal to? Anyone tell me in the chat? If I want constructive interference. So most people are saying m lambda, which is correct. And if you set it equal to m lambda, then your condition, the correct answer, will look like this, right? Basically dividing by 2 on both sides, I will have L1 minus L2 equals m lambda over 2. This looks like the wrong answer because you see a half integer wavelength sticking up there. And when you see a half integer wavelength, you think, destructive interference, so D can't be the right answer. But the reason it is the right answer in this case is because of the geometry. The light is traveling basically twice that distance L1 and twice that distance L2. And that factor of 2, as you can see, ends up being what causes this to look like that you're asking for an integer number of half wavelengths. Okay, so this kind of device can be used to measure very small distances. And in fact, I was just poking around a little bit on the web and I saw that you can buy for an undergraduate laboratory a device like this that can measure picometers. So that's 10 to the minus 12 meters, which is very, very small distance. A large group of physicists and astronomers and laser physicists have put together an experiment called LIGO, which stands for Laser Interferometer Gravitational Observatory. And it uses lasers, really powerful ones, and very long interferometer arms. And I didn't define what an arm is, but in this diagram here, L2 is one arm and L1 is the other arm. And if you remember from that video I showed you, those arms in that tabletop experiment were sort of like 10 centimeters long. Here, the arms are 4 kilometers long. So these two photos on the right-hand side show the 2 different laboratories, one in Washington State and the other one in Louisiana, where they built 2 essentially identical interferometers, each with a pair of 4 kilometer long arms shown there. And then there's another one over here. And there's another one you can't see. It's going off in this direction in that figure. So the laser is in the building in the center or where the 2 arms meet. And then what these 2 arms are there for, at the very end of each arm is a mirror. And what they can do is they can detect distortions in the length of one of the arms that's as small as the diameter of a proton divided by 1,000. And this is sensitive enough to detect the compressions and expansions of space itself that are due to gravitational waves produced when black holes merge or really dense objects like neutron stars merge together. As these 2 objects circle around one another in orbit and get closer and closer and then merge, they basically bend space-time and cause this these outgoing gravitational waves that can then be detected basically at the very last minute, right before the two objects merge. And you can see this distortion. And this probably won't work so well, but if you look at that that figure, so it's actually much smoother on my screen here. I don't know how to slow this down so that you can see it happening. It seems like you're only seeing certain frames of this animation, but you're seeing the important ones actually. So the passing gravitational wave stretches and expands space as shown by those dots. So as the wave passes over the detector, it stretches out one of the arms while compressing the other one. So you get this effect where, let's see if I can start this again and maybe get a different pattern. Yeah. So you can see down below the photon detector gets bright and then it gets dark and then bright and then dark, depending on whether there's constructive or destructive interference. And I'm sorry that animation doesn't work better than that. I can post it if anyone's interested so you can see it in its fuller glory. Okay, so I'd like to now transition to start talking about ray optics. But before I do that, there were a couple of questions in the homework. And that last question is sort of the mini survey about radians and about the small angle approximation. So I want to just do a little aside and explain when to use radians and when to use a small angle approximation, and also a little bit about arc length. So you can safely use radians to describe an angle basically in all instances. The problem is that degrees are more familiar. So we tend to use degrees instead, but you can't use them all the time. And in particular, when you're talking about arc length, like this expression over here, you need to use theta there in radians and not in degrees. Regarding the small angle approximation, there's no fixed angle that you need to get smaller than in order for the small angle approximation to be correct. It's an approximation, so when you use it really depends on how much error you're willing to tolerate. Generally speaking though, if the angle is less than 10 degrees, it's small enough to use this approximation, where sine of the angle is and the tangent of the angle are roughly equal to the angle itself. And again, this angle would be in radians. And for the two-slit interference and the single-slit diffraction that we've been working on in this class, the small angle approximation is a good one. But for diffraction gratings where the angles can easily be 20 or 30 or 40 degrees for where the fringes are located, then the small angle approximation will not work so well. So the figure on the right shows an illustration of how we could start thinking about arc length. Some people have questions about that. So the arc length, you may remember the formula is S equals to R times theta, where S, R, and theta are labeled in that figure. And one way to remember this formula is as the angle theta goes from having some small value shown here over to a value of 2 pi, all the way around like this, then the arc length will be 2 pi times r. In other words, if you go all the way around a circle from here all the way around, then you will have an arc length that's equal to the circumference of a circle, 2 pi r. Likewise, you can think of this arc length in the approximation for small angles. So as you shrink down this angle theta, this little triangle here, the bottom of the triangle, length, even though it's a straight line, becomes more and more closely equal to the length of the curved arc length S. So as that angle shrinks, sine theta becomes roughly equal to S over R, which is equal to theta. Okay, so I'd like to now start on a new topic called ray optics. And this is a way of describing light that's sort of halfway in between wave optics, which we just did, and treating photons as particles, which is what we'll do when we get to quantum mechanics. Whereas light is indeed a wave under many circumstances, and it's also a particle under many circumstances, it is never actually a ray. So the idea of a ray is more of a mathematical construct. It's not real, but it's really useful in allowing us to model the way light will behave. The basic idea is that a light ray shows the direction along which light energy is moving or flowing. So the characteristics of these light rays are that, first of all, they travel in straight lines. They can cross one another. They travel forever in the same straight line unless they interact with some matter that causes the light ray either to be bent or reflected. And we'll talk about that in more detail shortly. So an object can be a source of light rays, and there are two main types of sources that we'll consider here. One, the rays can be emitted by a luminous object like a laser pointer, or the light can be reflected like when the sun shines on a tree. So the tree then reflects all that light, which we then see. Now those light rays in both cases go out in many directions. We're only aware of the light rays that actually go into our eyes, or that enter a camera or some other device. So in other words, a laser that is pointed parallel to the front of your face and that travels by, it could get arbitrarily close to your eyes, and you will not be able to see it. Right? A laser beam is just going straight across. It's only if there's some dust particles, like if someone bangs an eraser in front of your face, which wouldn't be very pleasant. But then when the laser goes through there, some of the laser light will reflect off of the chalk dust, and then you'll be able to see it. But if there's no chalk dust and no dust in general in the air, that light ray can go right by you and you would never see it. So the ray has to enter your eye in order for you to see the source of the light. So generally speaking, light rays come out in all directions from an object. But if we tried to draw all those directions and all those light rays, we'd end up with sort of a meaningless blob of arrows, as sort of shown by this little figure here. So what we do is we judiciously choose a handful of the rays, namely the ones that are going to be detected or seen, depending whether it's a camera or your eye or whatever. And an example of this is illustrated over here with this pinhole camera. So the pinhole camera has a tiny little hole shown here, and light goes through that hole, and then an image is formed on the other side of the pinhole camera, on the right-hand side of it. And so one question you could ask is, what will that image look like? Will it be upright or inverted? And how big will it be? And you can figure all that out from using light rays and basic geometry. So if you start out with looking at the rays that come from the top of the tree, you can see that this ray makes it through the pinhole, and then it ends up down there at the bottom of the pinhole camera, on the screen of the pinhole camera. And in a similar way, you can think of the light that's coming from the trunk of the tree, and it will end up here at the top of the image that's in the pinhole camera. So immediately from this very simple diagram using light rays, you can tell that the image is going to be inverted, So in other words, the tree is going to be upside down. And with a little additional work, knowing the height of the tree and the distances involved, you can figure out what the height of the image will be. Sorry, that's got chopped off of this figure. What the height of the image will be inside of the camera. Conversely, you could use this if you measure the image inside the camera, you could figure out how tall the tree is. And that would just be simple geometry, you know, it's similar triangles basically. Okay. So the first subject we're going to consider is reflection for light rays. We're only going to consider specular reflection. And what that means is reflection off of smooth surfaces so that the light bounces off in a predictable way all across the surface. So in these cases, the angle of incidence equals the angle of reflection. And that's shown in this diagram here. So there's an incident ray coming in from the left. It bounces off this reflective surface. It comes in at an angle theta I with respect to the normal. And the normal is another way of saying perpendicular, and that's indicated with the dashed line. That dashed line is perpendicular to this reflective surface. And then it bounces off, it's reflected at an angle theta sub r, the angle of reflection, and that reflected ray bounces off at an angle of reflection that is equal to the angle of incidence. So in other words, theta I equals theta r. So that's the rule for specular reflection. So let's apply this to a common everyday object, the mirror. So if you look at the reflected image in a mirror, you realize that the image, it could be your face, looks like it's behind the wall where the mirror is mounted. So how do we imagine this is happening, and how can we make it more quantitative? So if you have an object over here labeled P, and that could be, for example, you know, your nose, and light is reflecting off of your nose, and then there's a mirror just here that you're looking in. That light will bounce off of your nose towards the mirror following this path here, where the angle of incidence will equal the angle of reflection. And what happens then is, if you're looking down here somewhere at what's going on, you will see this light ray come in, and you will say, it must have come from back here, because whenever I see light, I imagine that it's coming at me along a straight line path, straight directly at me, and therefore I will extend this ray back to this point here. So that's why you say that the light is coming from behind the mirror. And if you do a little more, whoops. Sorry. Shrink that down, so I'm going to rotate that. Kind of fussy. All right, that's good enough. If you look at a bunch of rays, it becomes a little clearer what's meant. So if you look at these rays that are sort of coming out at various angles, these two I've just drawn, you wouldn't see, but I'm just trying to show you that these rays are coming out at different angles. And then you extrapolate them each back along those dashed lines, you'll see that they all converge on this point P prime, which is behind the mirror. So your eye or a camera will say, oh, well, these rays are coming as if from this point P prime. So this is known as a virtual image because the light doesn't actually come from the image's location. The light is actually coming from this object P. It looks like it's coming from this point P prime. but it isn't actually coming from point P prime. So this is called the virtual image. Just as a side note, my million cats actually think that all images are real and will stare at mirrors for a long, long time given the opportunity. So let me do this concept question here with you. So this is a question about reflection. And the question says, when you look into a plane mirror, what do you see? You see a real image, you see a virtual image slightly smaller than your true facial dimensions. You see your face just as someone walking by you on the street would see it. You see your face left, right, reversed. Or you instinctively say, mirror, mirror on the wall, who's the fairest of them all? Okay, put your answers in. All right, so most people said D, which is correct. I'm going to finish up in just a second here. You will see your face left to right reversed. And one way to imagine this is if you have a blue and white stripe on your right cheek. When you look in the mirror, the image that you see in the mirror will have those stripes on the image's left cheek. So you could ask, what mirror configuration will change this and allow you to see your face as everyone else sees it? And the answer is a perpendicular mirror configuration like this. And we'll explore how many images are formed by two perpendicular mirrors as sort of a separate activity next time. Okay, thanks very much. I'll stick around if anyone has more questions. Have a good day.
Hey, do we still have lab, even though we got the quiz on Thursday?
Yes, there's still going to be lab.
All right, cool. Thanks.
Yep.
Does the material for quiz 1 end right before we start interferometer stuff?
Yes, that's correct.
Okay, thank you.
Yep.
For our lab reports, only one person needed to submit the report, right?
I'm not sure how that is done. It might be different for each lab. You should either ask your TA or Dr. Van Hook, please.
Okay.
More cat examples. Okay. All right, if there are no other questions, we can finish up. Bye, everybody.
I have one more question, sorry.
Oh, okay, go ahead. Yep.
Sorry about that. Are there going to be a like a practice set on mastering for this quiz, or are we just going to have our homework questions to look over?
That's a good point. I will try to put together some questions on mastering as extra practice. Thanks for reminding me about that.
Thank you very much.
Make a note about that. Okay. Yep. I'll see what I can do.
Thank you so much. Have a great day.
You too. Bye-bye.
Thank you.
Dr. Code,
Yes.
are we allowed to use tablets in the quiz for this Thursday?
I'm sorry. Can you speak up? It's hard for me to hear you.
Sorry, are we allowed to use tablets to do our work on for the quiz this Thursday, or should we do it all on paper?
I think you're going to have to do it all on paper, but I'm not 100% sure of that.
Okay. Well, it's through Canvas, right? Like the submission stuff, like the questions are on Canvas?
Yes, the questions are on Canvas.
Okay, so we submit like no PDFs or anything like that. So yeah, I should just use paper then.
Yeah, right.
Okay, all right, thank you.
You're welcome. Any other questions?
Professor, if the exam we're gonna have to do it on paper and then and then scan the pages and submit a PDF of the.
No, you don't need to scan anything. It's the questions are all multiple choice on Canvas, and you can do whatever work you want,
Okay.
but we do not look at the work.
Okay, all right, thank you.
Welcome. Any other questions? Okay. Bye-bye, everybody.